Assalamu alaikum YouTubers, welcome back to SLK Tours. Here in this section, we'll be just designing a one-way slab. Remember, this is RCD, reinforced concrete design. But before starting the design calculation, let's see what's one-way slab. Just look at the same picture for a moment. You can clearly see the slab is just bending in one direction. And it's of course supported on two edges. So the slab is just a one-way slab. Because a slab is known by a one-way slab when a slab is supported on two edges and bends in only one direction. But remember, only bending in one direction and the slab supports can not only just define the slab as one-way or two-way. Because what will you say about the same picture, this one? Is this one-way slab or two-way slab? Actually, I can't decide now because I don't know what are the dimensions of this slab. If it's square, then of course I can decide it's two-way. But if it's not square, it's rectangular, then I can't just decide it's one-way or two-way. Because if I say it's one-way, you can clearly see it's supported on four edges. And in one-way slab definition, we learned the one-way slab is always supported on two edges. What should I do now? This is why the length to breadth ratio come into play. So even when a rectangular slab is supported on four edges, the slab may be considered as a one-way slab if the length to breadth ratio is just equal to 2 or greater than 2. Let me just draw the plan of the same model. Say this is a rectangular slab with length equals 20 meter and the breadth equals 10 meter. Now is this one-way or two-way? Of course I can decide it's one-way, because 20 divided by 10 is just equal to 2. And look at the step 2, we learned when the length breadth ratio is just equal to 2, the slab is known by a one-way. Also remember, in design, a one-way slab is designed for the spanning direction alone. The main tension reinforcement bar of such a slab run just parallel to the span. This is a nice technical term, okay? And a minimum amount of shrinkage reinforcement is provided. The shrinkage reinforcement is also known by temperature bars or distributions bar, no problem. But what does this mean? The tension reinforcement bars of such a slab run parallel to the span. It means when we just distribute the tension bars in the slab, the tension bar will be just run parallel to the span like in this palm. You can clearly see these red lines just represent the tensions bar. So this is the direction of main or tensions bar. And what's the direction of shrinkage bars? Of course, they will be just opposite to the main bars, right? Like, of course, in this palm. So up to here, you just learned the definition of a one-way slab. Now let's go for design, okay? And of course, I'll give just a solution to an example. Here we have an example. This is example 1. We are just asked to design a one-way slab if the concrete strength FC prime is 4 KSI. The steel grade or FY is just 60 KSI. The live load is just 220 PSF. The dead load is just the self weight of the slab. And of course, the span of the slab is just 10 feet. I think this data is just enough to design a one-way slab. If we need any assumption, we'll of course do them, right? Now let's go for a design calculation. And this is a continuation of the example. And of course, we have some given data. Say these are just the supports and the slab. The span is just 10 feet. And remember, the design of a one-way slab is just the same we do the design of a rectangular beam. So I'll just design the slab only for 1 feet strap, right? The weight of the strap will be just 1 feet or 12 inches. So I'll design the slab only for 12 inches and then I'll of course apply the 12 inches design to our all slab. Remember, we have FC prime 4 KSI, FY 60 KSI, live load is just 220 PSF. We also know the dead load is just the self load or self weight of the slab. Now let's come to design solution. In the design solution, let me just assume the effective depth will be just the total height of the slab negative 1 inches. This is my assumption, right? Purpose time, no problem. But what's the effective depth and the overall depth or the overall height of the slab? Let me just take a section of this 12 inches slab, like in this palm, with reinforcement. And the total height, just look at this section. The total height just represent the h. And the effective one is just, of course, the distance from the center of tension bar up to the upper fiber of the slab. But why 1 inches? The best value per concrete cover is just 3 or 4 inches or 0.75 inches. Per this time, remember the effective depth is just from the center of main bar. So half diameter will be also taken, right? Half diameter plus this concrete cover will make just 1 inches, right? So by this time 1 inches is of course a good assumption for me. So the effective depth will be just the total height negative 1 inches, right? But the total height is also unknown. What should I do now? Remember, for total height, the minimum height of the slab may be just taken from the same table. Table 13.1, this is the table for minimum thickness of one-way slab, right? I just took the screenshot of this table from a nice book, Design of Concrete Structures. I think it's just written by Nelson, maybe. Yeah, the other name is Nelson. So it's a nice table, okay? Just look, when a slab is simply supported, we can take a minimum thickness is the total span divided by 20, right? And there we have, of course, 3 other options. But our slab is just simply supported, so I'll take the minimum thickness is just span by 20. So it's just L by 20 and the length is given, which is 10 feet divided by 20. This will give me answer in feet. I'll just multiply with 12 so I can get the answer in inches. So H minimum is just 6 inches. So the total height of the slab is just 6 inches. And what will be the effective depth? Just subtract 1 inches, right, from the total height of the slab. We can get, of course, the effective depth, which is just 5 inches. Now the dead load determination is quite simple. So I'll just calculate the dead load, which is the self weight of the slab, right? So the dead load will be equal to just the density of the concrete times the volume of the slab. But the volume of the slab will be just the volume of this 12 inches strip. So volume times the density or the unit weight of the slab will be just the dead load. What's the unit weight of RCC? Remember, it depends on the mix in the steel, okay? Per mile steel in the mix just is a normal. Of course, the unit weight may be just from 145 to 150 pounds per CFT. So I'll take, this is of course RCC, so I'll take 150 as a unit weight, right? 150 pounds per CFT. So 150 times BH. This is the cross-section area of the strip. Now you may wonder, B times H is just the cross-section. Why should not I just multiply with the span to get the volume? But I'll not just multiply this with 10 because I'm not looking to the beam. I'm just looking to the slab, okay? And this is a flat slab. So I can get the dead load equals 150. To convert 150 into kips, we just divide this by 1000. We can get 0.15 times the breadth is given 12 inches or 1 feet times the height is given 6 inches or 0.5 feet. So we can get the dead load equals 0.075 kip per feet. Now just look at the live load. The live load is just 220 psi. So I should just convert this guy into kip per feet, right? So live load equals 220 psi is just 0.22 kip per square feet. I just need the unit to be in kip per feet because the dead load unit is just in kip per feet. I'll just multiply this guy with 1 feet. So 1 feet and 1 feet will cross each other. So I can get, of course, 0.22 kip per feet. So of course I got the live load equals 0.22 kip per feet and the dead load equals 0.075 kip per feet. Now I can just calculate the design load, right? We have of course 2 types of loads, the live and dead. So I can use of course an I-spector, 1.2 dead plus 1.6 live. So plug and chug in, we can get the design load equals 1.2. The dead load is just 0.075 plus 1.6. The live load is just 0.22. We can get of course 0.442 kb per feet. Now what will be the moment? The slab is just simply supported with uniformly distributed load, so we can get the maximum moment at the midpoint equals WL square divided by 8. Plug in check in, we can get of course mu equals 0.442. The L is just the span, which is 10 feet, so 10 square divided by 8, we can get of course 5.525 kb feet. If I need to convert the value into kb inches, I'll just multiply the same digit with 12. I can get of course mu equals 66.30 kb inches. Now when I have the moment, of course I can calculate the rho, which is the required reinforcement ratio. And for this I have a long expression, right? 0.85 fc prime divided by fy, 1 negative square root of 1 negative 2 times moment divided by 0.85 theta fc prime bd square. It's a long expression. Remember from the previous lecture, when we were just designing a rectangular beam, you have already learned bd square equals blah 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 blah. Actually, the above formula is just the rearrangement of this below formula bd square blah blah blah, right? To know better about this formula, of course you can watch the previous lecture, the design of a singly reinforced concrete beam. I'll come to my required rho, right? So the required rho 0.85 times fc prime is just 4 ksi divided by fy is just 60 ksi, 1 negative square root of 1 negative 2 times moment. The moment is just 66.30 divided by 0.85. What's the theta now? Let me just assume it's 0.9, okay? And this is a pretty nice assumption over here. So 0.9 fc prime again 4 ksi. The breadth is just 12 inches because we are just designing this guy for 12 inches breadth times the depth, which is the effective, is also known. So pipe square or pipe times pipe. The required reinforcement ratio equals 0.0042 So we got the rho equals 0.0042. Now of course I can calculate the required steel area. Per main steel we have of course rho times the BD. Plug in check in, we can get of course 0.0042 times the breadth is just 12 and the depth is just 5. So we can get 0.255 square inches as the main steel area. And per temperature or shear and cage reinforcement, we have a nice plug-in check-in. Let me just do this guy from a nice table 13.2. I just took this screenshot from the same book, right? Design of concrete structure, written by Nelson. Now let me pick a nice option. And these are of course the minimum ratios of temperature reinforcement, right, in a slab based on cross-section area. If you look at to the step 2, I think this is the best choice for me now, which is 0.0018. So I'll take this guy, okay. So 0.0018 BH will be just temperature steel area. We can get of course 0.0018, the breadth is 12 and the H is just 6. So we can get the temperature steel area equals 0.1296 square inches. After this approach, I can get now the reinforcement pattern. And the reinforcement pattern means the number of bars and their spacings, okay. So let me do this guy first for main steel. And the maximum spacing according to ACI will be just the minimum of 3H or 18 inches. So the maximum spacing will be just the minimum of 3 times 6 or 18 inches. And 3 times 6 is just 18 and 18. So the minimum is just of course 18. And for temperature steel, the maximum spacing will be the minimum of 5H or 18 inches. So this guy may be just 5 times 6, which is 30 or 18 inches. So I think 18 is just less than 30. We can get the maximum spacing equals 18 inches. But remember, this is the maximum spacing, okay? It's not our required spacing. So what's our required spacing? Let me do this approach in a nice table, okay? And let me pick a few options per main bars and distributions bar or temperature bar, okay? And here to get some options, we have a nice table from the same book written by Nelson. And this is of course table A3 area bars and slabs. Now let me just pick a few options now, right? Help me out over here. Our main reinforcement area was just of course 0.225, which is just near to 0.26, right? So let me just pick a nice option first in number 3 bar and come down 0.26. Yeah, this one 0.26, and the spacing will be 5 inches. So number 3 bar at the rate of 5 inches center to center. This is one option. Let me pick another option in number 4 bar. And number 4 bar we have 0.26 square inches and the spacing is just 9 inches. So number 4 bar at the rate of 9 inch center to center. What's your decision now? I think the best choice will be number 4 bar at the rate of 9 inch center to center, okay? So I'll say the main bar will be just number 4 bar at the rate of 9 inch center to center. Now let me pick a nice option for temperature bars. And the temperature bar area was just 0.1296 square inches, which is just equal to of course 0.13, right? And 0.13 is just of course just much least, okay, with respect to main steel area. So if I just pick number 3 bar, 0.13 is just over here, the spacing will be just 10 inches center to center. And this is of course a best choice for me now, okay? Because there is nowhere to do else except this one, okay? So I'll say use number 3 bar at the rate of 10 inch center to center, just for temperature bars. And this is called the design. So here is our result, okay? These are supports. The span is 10 feet. The concrete cover is just 3 by 4 inches. This is the main steel, okay? Just parallel to the span. And they are just number 4 at the rate of 9 inch center to center. And these are just temperature or shrinkage bars. These are of course just number 3 at the rate of 10 inch center to center. And the total height of the slab is just 6 inches. And this is it. I have done it. Now it's your turn and do the same, okay? Just change some videos and do the same process. You will get the same result. Thank you guys for watching. See you next time and wassalam.